Okay, so welcome to this lecture, and this is the second and the final talk of Tanja. So.
Thanks for the introduction. Yeah, so the second talk, so in the first week, you got already some bits and bases for time and frequency metrology. So Subhadeep was teaching you about the primary frequency standards, microwave clocks. You heard about atomic laser cooling of atoms. With Martina, you heard a lot about the ions, the trap particles. That's why I chose last week to teach you a bit about the ultra-stable lasers and the frequency combs to complete this. Today, I want to also briefly touch on how we compare clocks. So very briefly, transportable clocks and long-haul links. But before we jump into the clock comparison thing, I want to recap here the atom and ion, the clock business. Last week, I talked very conceptual about the principle of optical clock operation, what you need and what you can achieve. But I didn't have time to really give you like a concrete status. Yeah? And after my talk, I was approached by many of you and discussions about why do we need multi-ion clocks and are they at all competitive? So I really want to show you now a status update and a report of how this clock is working. So this is how it looks like. We started actually pretty late. So the setup we started in 2018, not so long ago. This is our 2 PhD students who are setting up the vacuum chamber. You see how it looks in the lab. This is our beautiful ion trap with the cooler crystal inside, the indium and the terbium oven, or the wires. It's all pure titanium chamber to get the best vacuum. Well, why did we choose indium? Well, what we like about indium, it's a very heavy ion. It's a very relativistic ion. So if you have a heavy mass, actually time dilation is not, it is a problem, but not so big as for the light ions, because time dilation scales with the kinetic energy divided by mc squared. And you see, you already win a lot if you have feeding rates, micromotion. A heavy mass helps you a lot. And I told you last week that optical clocks at the moment, or also in the future, are always limited by time dilation. So that's why when we started out in 2012, proposing the multi-ion business, we choose a very heavy atom. Well, the black body radiation shift of the indium clock is very low. Even at room temperature, we have only 1 × 10⁻17. So you will see later on that with a good, reasonable control of your experiment at the Kelvin degree, you can push this shift to the 10⁻19. It's not a problem, even at room temperature. You don't have to go cryogenic. And if you look at second order Zeeman shifts, you will see that the indium atom, thanks to this very large fine structure splitting and a very weak coupling, is actually the lowest one among the known clock candidates right now. So yeah, more than an order, factor 20 almost better than the aluminum quantum logic clock, and orders of magnitudes better than the ytterbium 171 clock. And this is actually also very important, as it turns out now, because now many people are complaining about the magnetic field, uncontrolled magnetic field in ion traps, giving them some large unknown second order Zeeman shifts. Well, we don't have this problem because we're orders of magnitudes less sensitive. And last but not least, what's also really lovely in indium is you have a direct detectable transition, even though it's an intercombination line. It's a triplet it's a singlet S0 to triplet P1 intercombination transition, but it's very broad. It's 360 kilohertz, so you can scatter off a lot of photons, and you can even directly cool on it and detect, of course. So that really makes it a truly scalable system. And at the time when we started out, we thought, okay, if we want to make this benchmark and then demonstrate the world that multi-ion operation is possible, we choose a simple approach, and that is the indium ion. I'm not saying it's easy because 230 nanometer and 236 nanometer for sure is not the most convenient laser to work with. But all these things adding up, making it, I would say, the first simple approach to the multi-ion business. Later on, we will also scale it up with ytterbium ions. But this is what was the first proof of principle we wanted to convey. And maybe a question to you guys, why do you think are these very forbidden singlet S0, triplet P 1 and triplet p0 transitions allowed at all, because last week we were saying if it's a singlet to triplet system, so where the spin of the electron has to change, it's highly forbidden. It wouldn't be allowed at all. And nevertheless, what we're seeing here are finite line width. So does anybody have an idea where this non-exclusion comes from? What makes this transition allowed suddenly? Any idea? No? Well, the indium ion has a large nuclear spin. I is n half, is 9½ Yeah? The nuclear spin gives rise to a very strong magnetic field at the nucleus, Tesla levels, yeah? Several Tesla of magnetic field in the nucleus. And this magnetic field couples and mixes the states here. These are not good eigenstates anymore, the way I'm writing it. Yeah? So you have a M1 transition, a first order magnetic dipole coupling between these states. And the triplet P1 state is again mixed with the singlet system because of the heavy mass of the indium. Indium has 115 units. So this again makes these eigenstates not really pure. You have admixtures on the level of 10 to minus 5, but that's enough to give you a really significant large line width. So first of all, you mix these two states, and then the nuclear spin mixes that two states. And that's actually a trick that was also proposed for the strontium lattice clock, because many people would actually prefer to work with strontium 88, with the bosonic isotope. But the problem is that there, if you have a bosonic system, it's totally forbidden. If you don't have a nuclear spin, these type of intercombination lines are just completely forbidden. But if you apply a magnetic field from outside, you can do the same trick as here comes for free from the nucleus. You as an experimentalist can apply a magnetic field and mix the states. That has been proposed and also been demonstrated. The only problem is if I, as an experimentalist, if I apply a magnetic field, I have to make sure that it's really stable in time. Otherwise, I have a problem with my clock. If I get it out of the nucleus, it is stable. There's nothing more stable than a nuclear spin. So this is the beauty of these systems where you have a nuclear quenching of these intercombination lines. Well, now I've told you that we were planning to cool directly on this forbidden intercombination line, but since it's still not like tens of megahertz, what you otherwise used when you do laser cooling of atoms, we want to go to large Coulomb crystals. They have been also called Wigner crystals. I'm more on the side, I agree, Wigner crystals, Coulomb crystals, for me it's really the same. I see the same type of phase transitions happening. But I know that these highly nonlinear systems with a long-range Coulomb interaction, they are very chaotic. And in order to cool them really to the ground state, you need very strong cooling power. And the cooling power needs to be actually larger than ytterbium-171 can deliver. And that's why we choose to cool it with ytterbium-172, just as a sympathetic cooling ion. So we cool indium ions with ytterbium ions. And since we already have them, we also use them as in situ probes to do in situ measurements of micromotion, characterization of B fields, and sensing of intensity profiles. It's a dual species clock, where you have a big lever, like indium is very insensitive as the clock ion, but the ytterbium ion can be very sensitive to magnetic fields, micromotion, and many things. So you have an in situ sensor in your clock. So you get everything for free. And this is how our small Coulomb systems works, because since we're aiming at 10 to minus 19, we don't want to throw in thousands of ions, maybe in the future. But we go bottom up, yeah, ion by ion. We want to start in small scales. So these are the typical Coulomb crystals that you see in our systems. And you see here the mixtures of ytterbium and indium ions. And another question for you, maybe a quiz question, who was paying attention to Martina's talk about ponderomotive potential and ion traps. So who knows which color is which? You see violet atoms and you see blue atoms. Which one is indium, which one is ytterbium? You can see it. Can you distinguish indium and ytterbium? Please try. Blue is ytterbium, yes, that's correct. And now why? Huh? What? Whoa. No, but this is not, this is different colors. No, this is misleading. Okay, I should have cheated you. This is not a good physics question answer. No, but these are different colors. I was thinking the very different color codes. No, but why is blue ytterbium in this pink and blue systems? Why is it ytterbium? No, nothing. It's just a false color image. Look at that. What do you see here? There's a phase transition. The pink ions are almost rounded up in a very narrow line. The blue ones are buckling out into the zigzag. And you see already here, the pink ones again they have a smaller amplitude than the blue ones. There's the phase transition setting in between one-dimensional and two-dimensional polar crystal. And if you look at the ponderomotive potential, so the ponderomotive potential of the ion trap is proportional to 1 over the mass. So the heavier the mass, the weaker the confinement. The lighter the mass, indium is lighter, the stronger the confinement. Ytterbium is heavier, the weaker the confinement. So the heavy guys, they buckle out immediately, while the lighter ones are confined. There you see the typical characteristics of a ponderomotive RF potential in an ion trap. Okay, so don't worry, not too many quiz questions anymore. Now I just want to show you, we invested a lot of time in building the best ion traps in the world for our clock, because if you want to reach 10⁻⁹, the ion trap is the big limitation, especially if you want to scale up to large Coulomb crystals that are spatially extended. You need a very good ion trap with very low micromotion, very low heating rate, and a very good heat management. We have seen that sometimes you have to apply 1000 volt RF, and that gives a lot of dissipation in the dielectric material. So we did a lot of engineering to have the lowest warming and heating of the ion trap below 1 Kelvin actually. When we drive it at 1000 volt, everything heats up to less than a Kelvin, delta T, less than a Kelvin. We did infrared spectroscopy, infrared measurements on the ion trap, and very complicated things. You can read everything in this kind of papers. That was a very long work. Also Infineon, the companies picked up on this, because if you want to go put your ion trap in a cryostat, you also need a very good heat management. Then here, if you look at the heating rates, Martina introduced it in a very nice way. And you see, I mean, this is this great paper from Mark Braunert in the Innsbruck group, where this is the whole worldwide ensemble of ion traps, cryogenic ion traps, and these are the thermal room temperature ion traps. In principle, there's something like a 1 over D4 or 1 over D2, depending how you fit it. There's some trend, but the scatter is huge. The scatter, maybe you can't read it, it's almost 4 orders of magnitudes. At the same geometry, the scatter observed is over 4 orders of magnitudes. And this is our ion trap here. So we're really at the very lowest line, just next to the cryogenic ones, but we're operating at room temperature. And also micromotion was minimized by finite element simulations to really use as many symmetries as possible to have really perfect micromotion. And I want to show you this picture. Maybe I'm very bad in doing paintings of 3D crystals, but that should be a Coulomb crystal. This is an actual measurement of 14 ions in a Coulomb crystal, atomically resolved. And we spectroscopically resolved the amplitude of micromotion in such an atomic Coulomb system, in such a crystal. And you see that each atom has a different motion. And this ellipsoids you see here should indicate the motion in 3D in X, Y, and Z. These are really ellipsoids. And if you look here, these are the distance between the atoms. But this bar is 1 nanometer. So this is the resolution of the micromotion amplitude. And you see how there's a tiny, tiny gradient over this atomic system. And that tells you that actually the time is ticking differently for each atom in this Coulomb crystal. Every atom feels a different time because of time dilation. If you're moving, if you have some finite motion, you have a time dilation shift, as I showed you before, the kinetic energy divided by the rest energy. And this is the critical thing that we have to control at the level of 10⁻⁹ and better for our clocks. And now this looks a bit boring because here you see 400 micrometer in spatial extension at the level of 10 to minus 19. But that was a long work. Yeah, it took us like 6 years working for that. Because otherwise, if you have a normal ion trap, you have gradients that are like a vertical line. You don't even see the slope anymore. Just to give you an example, when the NIST built the first quantum logic clock, aluminum with magnesium, they had 2 ions displaced by 3 micrometer next to each other. And when there was a background collision and aluminum and magnesium swapped, then the clock was off by several 10 to minus 17. Just because the ions moved by 3 micrometer, the time dilation shift was 10 to minus 17. So 2 orders of magnitude higher than what we have over 400 micrometer. And that's a lot of engineering work that you get this very flat micromotion in this linear ion traps. Okay, and then in 2019, we published the first estimated error budget. And I always emphasize estimated because an error budget is always just as good as the paper where it's written on. Yeah? You do your best, you do many measurements, you measure many quantities in your system. In the end, you never know if you have overlooked something. Maybe you have some terrible technical offsets that you don't know. But this is at that time, since the clock was not in full operation, locked to a frequency comb and everything, so we could only observe all quantities and estimate. And we published this in 2019, indicating for the first time that when we throw 10 ions in our ion trap, we can actually bring all quantities to the 10 to minus 19 level. This is the sympathetic cooling configuration. And this is the future vision, the prospective future, when we do direct cooling on indium, because that will bring us then to the ground state of the whole cooler system. And that will dramatically reduce the uncertainty in the time dilation shift. So this scenario would be is a Doppler temperature. This is what we're operating right now, the actual real clock, just the Doppler limit. With the ions, you're stuck at Doppler limit. The Sisyphus cooling is very hot. But this would be then a kind of a intermediate sideband cooling to the ground state, since we can cool directly on the indium line. And that's what we want to do next year. So we have now all lasers available. So this is what we want to try next year. But now is the big question, how do we know if the clock really has this performance? Yeah? How can we deduce the actual clock performance? So what's your guess? How do I know if this clock is right or not? I compare it with Martina's clock. But then, yeah, but yours correct, you see, and then it starts. This is exactly the problem that starts. Martina claims her clock is correct, and I say, but mine was more expensive, so this must be correct. And then we start fighting. So we need a third one, maybe Ian, if you have one. Doesn't matter, I mean, but we need a 3-corner head comparison, yeah? We need at minimum 3 clocks to compare so that we really can pick out the different performances of the individual clocks. It's the same with the lasers where you do 3-corner head, also the clocks needed. And this is at the moment worldwide the big limit because there are just not enough optical clocks in operation at this level. Yeah? This is many times we build a clock, we estimate an uncertainty, but we have nobody to compare to. So we need clock comparisons. And let's do clock comparisons via fiber networks. I show you why we need optical fibers, because already in 2008, when the first very good high quality optical standard came out, that was still, well, you see the first Rosenband paper, almost 10 to minus 14 in a second, but at that time it was a world record. But that was already orders of magnitudes better than any microwave link could do. So microwave carrier phase measurement via GPS satellites, this is orders of magnitude worse. This is what you use nowadays to disseminate the time worldwide, but it's a microwave scale. But for the optical standards, we do need optical links going through optical fibers. And the first proof of principle here at this level was done in 2012, actually by PTB and the Max Planck Institute in Munich, where they installed for the first time this long haul link of 900 kilometers or so from Braunschweig to Munich, and demonstrated this excellent performance of a long haul fiber link. And nowadays, you will see in Europe, there are more and more fiber links starting to grow. So this is just an old picture. But nowadays we have connected Braunschweig, PTB via Strasbourg to Paris, to the French Metrology Institute, up to London, to the NPL in England, down to the INRIM in Torino in Italy, and many, many more small fiber patches are now connecting up in a more and more grand circle of a unifying fiber network in Europe. And this is great because then we get more and more optical clocks in that we can compare to, and where's a probability that they have a high uptime and that they're running. And this is actually something very recent I want to show you that happened just last year in 2022, a European campaign called ROSIT, funded by European Metrology Network, where 3 optical clocks that we have in Europe were compared, PTB, INRIM, the Italian Institute, and CERTE, and the target was to compare it at the 10⁻17 level. Oh yeah, please. No, they stabilize it out actually. I mean, they stabilize it. They would see it, yeah. 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 But yeah, I mean, you're right. If the area was huge compared to the rotation, then it's true. Then there's a big effect. But at the moment, we only have to stabilize the fiber length, and you don't notice that. Yeah. Okay, so what I was saying, okay, so we have 3 clocks now. No, sorry, I messed up. So, what's happening? Okay, so we have different types of clocks now. So in Paris, we have a strontium lattice clock. In INRIM, we have a ytterbium lattice clock. At PTB, we had a strontium lattice clock, so they can directly compare. We have the ytterbium ion and now the indium ion clock. So locally, we have now 3 clocks for the first time, but it's really very brand new, very preliminary. And actually, big parts of it hasn't been published yet. I think this slide, Fritz probably showed last week in his talk, right? Because this is really a showcase of a current problem of metrology, that you think you have some of the best clocks in the world. You write down your error budget and it's 2 × 10⁻18. But then you measure against other clocks and suddenly funny things start happening. And what they saw is when they compared strontium versus ytterbium, at that time, these were the only optical clocks at PTB. Yeah, and they saw some funny jumps. Yeah, for a long time it was okay, and then once in a while jumps did occur, and they still do occur. And then the same happens. What Martina and I had, which clock is to blame? You don't know. And this is now really shows the importance of frequency ratio measurements, because even locally at PTB we can measure these 3 ratios, and then we have a number, and I can tell this number to somebody else. Yeah. And then we can also compare in a very simple way. Like when we compare now indium with strontium, fortunately also in Tokyo, there's now an indium strontium clock. So now I will show you the example of this very recent clock campaign happening 2021 and 2. And this is not published preliminary data, so take it with a grain of salt, but it will be published very soon this year. So we were running for the first time as a clock. In 2018, we started building the system. In 2021, we saw the first really locking of the clock. And the first thing we did, we measured against cesium. And this frequency ratio is called an absolute frequency measurement, right? Because cesium is the definition of the second. And then it was already quite interesting, even at that level, at the 10⁻16 level, you learn a lot. Because in the old times, indium was operated at the Max Planck Institute in Garching, at the Max Planck Institute for Quantum Optics, and they did the first indium measurement. At that time, indium was one of the best clocks in the world, but a long time ago. Later on, Erlangen made another measurement, but they disagreed, and they had this problem again: who is right, who is wrong? You don't know. Now, many years later, more than 15 years later, Tokyo redid it, and we in Braunschweig redid it, and we both agree. So we can pretty much say Erlangen was right, and we pushed down the error bars by a factor of 100 compared to the old times. Also in terms of optical to optical frequency ratio measurements. So NICT in Japan measured for the first time in 2020 indium versus strontium lattice clock. This was the very first time that anybody on this world measured this ratio. And this is this publication, and also, yeah, 2020 it was published. Now, 1 year or 2 years later, I mean, we also started 2021, we measured the same ratio at PTB against our strontium lattice clock. And thanks to our good clock laser that I showed you last week at 10 to minus 16, we improved immediately by 2 orders of magnitude. So we have now a frequency ratio measurement of indium versus strontium and indium versus ytterbium at the level of low 10 to minus 17, 2 orders of magnitude improvement. But this is still a single ion case, yeah? 1 indium ion, 1 ytterbium. This improvement really comes from a very good clock laser. And this is now the very preliminary result of this big European measurement campaign, where you have now many clocks at PTB, Syrte, INRIM. And honestly, what everybody sees here are really funny bumps, you see? The L deviation is not averaging down straight. For some clocks, it's not even crossing the 10 to minus 17 barrier. The bump is already here in the high 17 range. And I think last week for the diamond and V-center sensors, we also saw these bumps, air condition bumps. Everything is changing on a time scale of a day. Yeah? The students are coming into the lab, the house is warming up, the mechanic, electronicians taking operation machines, magnetic fields are fluctuating. So it's, if you don't control all systematic shifts well, you can be pretty sure that you have a bump at this time scale. And this is what almost all clocks do see. That's quite amazing. But then when we did our measurement against strontium, it was a 6-day measurement, a local one at PTB. I mean, it was not the first one. In the beginning, we also had the bump, I must say. Yeah? But then when we understood where the bump comes from, we were able to pin it down and average down to 3 times 10 to minus 18 in a straight line. And we just couldn't measure longer because we're construction sites and everything in operation and people want to go to sleep. But this is very encouraging. We don't see any flicker at the moment. So we're really averaging down in a very straight way. And this is certainly absolutely not easy to see this straight line. Huh? Yeah. Oh, because this is the laser. You see the clock laser. This is quantum projection noise of the atom. And in the beginning, when you compare clocks, you only measure the quality of your laser. But the laser is, of course, worse. And then this is the lock-in bump, that's the gain. So if you would have bad feedback parameters, then you even overshoot and then go back. So here you have to optimize the gain parameter. And this is now the atomic signal you see. And this is now the first error budget that was really benchmarked against the other optical clocks. So not, so really verified. And you see here, we're doing a bit worse now. We're at 2.5 10 to minus 18, but still not bad. But you see, you also have technical things like the servo error, technical noises, also AOM phase shifts. But actually the biggest contributions that we keep seeing right now is the black body radiation shift. And the reason why this is so large is of the unknown polarizability of the indium ion. Mariana Safronova calculated for us, but ab initio calculations are not at this high precision yet. They have 10% uncertainty. And these are this 10% uncertainty of Mariana's calculations. But at least we know it's constant in time. The polarizability is an atomic constant and will not change over time. And the same here, what we have here, the second order Seemann shift, static, it's actually the unknown gyromagnetic ratio of the ground of the clock state of indium. The Chi factor is not known. We also will have to measure it in the future and eliminate it. That's actually easy to do, but it's also an atomic constant. And if we look now at the uncertainty that we have right now, and sorry, this is a typo, that's 2.5, but the reproducibility, if we repeat the experiment again and again, counting on the constancy of the natural constants, yeah, then we have a reproducibility of 6 times 10 to minus 19. If I forget about the unknown polarizability in the Chi factor, then this is the reproducibility we have. And in the future, we want to push it down further to the low 10 to minus 19. This will be with the direct cooling of the indium ions. Okay, and then just a glimpse about the multi-ion operation. We haven't been working on this now for 1 year because we had a lot of construction, unfortunately. And just when we wanted to measure against strontium, strontium was down and the oven was empty. And again, you couldn't compare the clock. But what we can already tell, we have a very equal contrast over the whole Coulomb crystal, the same identical Rabi flops, the same coherence time. And we have logged and run the clock in a multi-ion operation with different configurations up to 4 + 8 ions. This was in the clock measurement campaign, but you see here, strontium was down and the oven was empty. So all we can say now is, at least with the clock measurement campaign, conservatively, we can say also the multi-ion operation is stable and accurate, at least the level of 10 to minus 17. But anything else, I would tell you here, we need more measurements to prove it. Yeah, we have to measure against strontium and really demonstrate it. Yeah, so I hope to have convinced you a little bit that, clocks are really breaking soon this border to 10 to minus 19. I mean, one did, I told you 9.5, 10 to minus 19, but more and more will do it. And we're really heading to the low 10 to minus 19. And now in the following, as I promised in the abstract, I want to talk a little bit about the applications. What do I do with such a clock? It's nice to have it in the lab, but what will be an application for it? And well, there's certainly a very technical application, timing and navigation. I will not touch on it, don't worry. I just want to show you one of my favorite clocks, the DSAC, Deep Space Atomic Clock by NASA and JPL, that was flying in orbit in space in 2019 for 2 years. But it's a microwave clock. It's a many-ion, multi-ion, ytterbium-ion microwave clock. Yeah, and a multiple trap, yes. And that's an experiment that was going on for more than 20 years. I don't even recall when this started, but that was a very long-term preparation. But it's wonderful. I mean, these clocks are needed for deep space navigation to really improve navigation of space vehicles, preparing the Mars mission and such things. But everything that was in orbit is so far microwave clocks. But I will not go into the technical navigation thing. For the sake of time, I was choosing these two parts, relativistic shortwave and fundamental physics. So let's start with the earthbound part, relativistic shortwave. And again, this boils back to time dilation. But now it's not the motional time dilation. Now it's the gravitational time dilation. So Einstein tells you that if you measure your time here and then you lift your arm and measure here, time is ticking faster. And if I put my clock closer to the ground, time is ticking slower. In a black hole, eventually time even stops and freezes out. And this is exactly this effect that we're observing with clocks on an everyday basis. My clock is in the basement of a building, and if I measure with another clock, I must observe the height differences. Otherwise, I get the wrong frequency ratio. So our ion is actually leveled in with millimeter precision. I know the height of my ion with respect of the geoid with millimeter. Our friends from the geodesy department did that for us. And this is now the exciting thing. Just to give you an idea, if you lift your clock by 1 centimeter, you will measure a time dilation shift of 10 to minus 18. And this is just about what we can do. And since we're heading to 10 to minus 19, we need to know the heights at the millimeter level. So what is this geoid, this potato I show here? Well, that's something that actually was invented by Carl Friedrich Gauss, who was the son of Braunschweig, where I live now. So I'm very proud of this, the one who also invented the Gauss unit, which was then taken over by Tesla. But I prefer Gauss because it's really a natural unit. Yeah, like the Earth magnetic field is half a Gauss. So that feels right. That's the right order of magnitude for me to live in. And Gauss was not only caring about magnetic fields, but he was a brilliant geodesist. Yeah, he did this uncertainty calculation, triangulation, everything what we know nowadays, the Gaussian distribution. And he proposed this idea of the geoid. He called it the Erdfigur in German, which is the equipotential surface of the Earth gravity field under gravity and rotation. So if you would imagine the Earth is covered just by water, no mountains, no land, then this is the shape the Earth would have, because water always follows this equipotential surface. And the undulation that you see here is on the order of 100 meters. This is, of course, exaggerated. But this geoid is not so well known. So if I would compare my clock in Braunschweig to the one at NIST, across the continents, there are height uncertainties of the order of 0.5 meter. And that's really critical. And if you see here, that's also a shocking big uncertainty or error. Ground-based measurements of the geoid compared to satellite-based measurements from satellite missions like Ghosh. And when you see a huge gradient over Europe from the north of Scotland to the south of Italy and Sicily, it's minus 0.8 meter to plus 0.4 meter, more than 1 meter offset along here. So much off are the ground-based geodetic measurements of our height system. And this geoid, the height system, determines the flow of water. So you can imagine it's also important for hydrology and for everything. And that's why I think it's a really interesting thing if we have more and more clocks connected via these fiber networks, that these clocks can really serve as new height references, that we can go away from this geodetic tide gauges, that you really try to measure the height of the Mediterranean Sea, the height of the Northern Sea, but the sea level is changing, the salinity of the water is changing, the tides are changing. So clocks are much more independent height references. And it was not me who proposed it, that's a very old idea, but the technology was not mature enough at that time. And so together with my colleagues at PTB and our friends, the geodesists, we had been writing some review article about atomic clocks for geodesy, if you're interested in that. There's also some interesting example what you can do. Another example, not just to give you a height reference system, but to really do geodetic measurements. For instance, if you bring up our clock on a mountain, the highest mountain of Germany is the Zugspitze, and unfortunately this mountain is shrinking. Because of global warming, the permafrost is melting and diminishing. So the subsidize, it's basically subsiding and really shrinking by probably 1 or 2 centimeters per year. The problem is that geodesists can't measure that because here the rough weather conditions, it's too noisy to have good GPS measurements with a high accuracy. If they bring up a gravimeter, the gravimeter measures short range variations with 1/r². That's the little g acceleration, the force that is changing with 1/r². A clock on the other side measures the potential, and the potential scales with 1/r. So you're only sensitive to long range mass changes. So if the mountain shrinks, you see it. The gravimeter on the other side only measures the snow cover changes over the year. In Europe, we have a lot of snow, we have a lot of water, groundwater tables are changing, and all these you see with the gravimeter. And you can't distinguish this noise that was plotted here, don't worry. You can't distinguish the noise that you see from the local mass changes over the year by the actual effect that the mountain is shrinking. So you see hybrid sensing of potential measurements and force measurements can be also very useful in such a case. And this is the summary. So I already mentioned it last week. For this type of relativistic geodesy, we don't need the most accurate clocks. Actually, here I would not care about the polarizability or about the G factor. I only need a reproducible clock. Yeah? I want to make sure that my measurement is reproducible and I can compare it differentially with another clock. Then we need networks of clocks connected either by fiber links or even ideally free space optical links. And we need very robust and compact portable clocks. And I think some of you are also researching in that. And yeah, I mean, this is not complete. These are just, I'm cherry picking 2, but there are many others. I mean, some of the first portable clocks were here, the PTB one, which is really in this truck anhänger here. And that was also doing some geodetic measurements with the INRIM in Italy. So this is in Torino, and they have been to the Alps, to the high Alps, and really measuring, because this is a really rollable clock. They can go to different geodetic sites and do the measurements. That was the very first time that people had demonstrated such an application of a geodesy measurement. And now, a few years later, Hidetoshi Katori did a wonderful experiment with this portable clock in Tokyo by lifting one of these clocks up to the Tokyo Tower by more than 400-meter altitude. This is a little bit different to do because he only has one clock laser. And since the clocks are directly on top of each other, he can do a differential measurement with a lot of common mode rejection using the same clock laser, but 2 different strontium clocks. That's of course not possible if you really roll around. Then you also need a transportable clock cavity. So it really depends what you want to measure. and this is for the guys who I've been talking to during the coffee breaks. I would say there also, if you want to build an iron clock, not a lattice clock, then the multi-iron approach also is rather relevant for portable devices because it much more softens the requirements for your local oscillator for the clock laser that you have in your truck and you want to carry it around. Maybe it should not be this 0.5 meter cavity with 500 kilograms of mass around it. Don't take the numbers seriously, this is just a rough sketch. So what I want to show you is if you have a single iron and you want to really exploit the lifetime, some of the best irons go for 20-second lifetime and long interrogation times to push the quantum projection noise limit. But then you have one measurement every 20 seconds, and you need at least 100 measurements to lock on it. Yeah, you need significant signal to have enough bandwidth, enough gain to lock onto the atomic signal, and that means you need a laser at the 10⁻17 level to average down. If you have more ions, just 10 of them or 100 of them, you can improve it by an order of magnitude and lock much faster on the atomic signal and average down. Or if such a thing is sufficient, you might even want to work with the laser at the 10⁻15 level and average. So this is a strength of having more signal and more qubits in your ion trap. And yeah, this is just for fun. During the COVID lockdown time, we had time for such things. So I was invited by Fermilab, NIST, and I joined up with them. We made a nice movie that was done by Bloomberg TV. It's all about time dilation. It's about relativistic Jourdacy, time dilation effects for fundamental physics, but on a simple level. And it reached actually more than 800,000 views already on YouTube. So it's a pity I didn't put any advertisement at any commercials. No, but you get money from YouTube every click. Okay, now this is a good point to switch subjects, switch gears. We are physicists, we're not working for money, we want to understand the world, right? And this is now what a really beautiful application that you have when you have a tabletop experiment. You don't have to go to an accelerator, you have a very good clock. Now we can do high energy physics and searching for new physics. And don't worry, I will not repeat what Dima Budka told you already, but I will build on it. So what I'm very excited about is to question and challenge the standard model physics, and not only quantum mechanics, but in particular Einstein's general relativity, which is so amazing. It always works. No matter what you do, it always works. It's frustrating somehow. At a certain point, we know there must be something. Yeah, why quantum mechanics and general relativity at the crossover, what happens really? And that's why we go to more and more precise measurements, and also nowadays with true quantum systems, single ions, perfect control quantum systems, to question Einstein's equivalence principle. And I will also mention quickly some dark matter models and tests for search for dark matter that we can do with our high precision measurements. But first of all, what is it, this Einstein's equivalence principle? Well, you see here the 3 pillars. The first of it is the universality of free fall, also sometimes called the weak equivalence principle. And this is very simple. You have for sure learned it in physics lectures. So if you drop in vacuum a hammer and a feather, Einstein says they fall at the same speed, the same acceleration. So the universality of free fall is telling you the trajectory of a point mass in a gravitational field only depends on the initial velocity and a position, but not on constituents. And people are, of course, questioning that. Yeah, it was not only Galileo who tested it in air, but nowadays we go to space, and from space measurements, we pinned it down to below 10⁻14. This is already rather significant. Then the next thing is local position invariance, LPI. That means the result of an experiment is independent of its location in space and time. That means if you have 2 different clocks, you could basically test this gravitational redshift. So if you have 2 identical clocks and you lift them, then you can question, is this prediction of Einstein correct? Kasturi did it in a Skytree tower in Tokyo. Delva et al. Did it with Galileo satellites for global positioning. So the European Space Agency launched a satellite into the wrong orbit. It was not. It was very elliptical, not useful for navigation, but very useful for fundamental physics. So this is where this bound comes from, 10⁻⁵. It's actually not so well tested, yeah, compared to the others, almost 10 orders of magnitude. Then another type of LPI is if you put two different clocks of different constituents, so different number of neutrons, for instance, yeah, and you have them exactly on the same level, and you compare them, and you see, is gravity changing? So you place them in different gravitational fields. Ideally, I would like to throw them towards the sun, to a very strong gravitational center, and see, is time still identical? Einstein, LPI would tell you it must always be the same, independent what type of clock you're using. And last but not least, the third pillar that I will dive in also a bit deeper is the local Lorentz invariance. And that's telling you the result of an experiment is independent on the orientation and velocity of the laboratory frame. So Lorentz transformations. Now, how do we test this? First, let's talk about, I will start with clock comparison. And this, I think, has been already there in Dima's talk, so I will not repeat it. It's just a reminder that there are many, many theorists now that are predicting a possible coupling of this dark matter scalar fields with standard matter. And that would mean that the fundamental constants could change over time, over location. They could even oscillate, yeah, by proposing such kind of scalar couplings. There are many, many possible scalar fields that had been proposed. But for us, operating a clock, it would give us a level that we really could look for a possible variation of the fundamental constant. And the type of fundamental constants you're sensitive to with the clock is, of course, alpha and mu. Alpha, the fine structure constant, mu is the proton to electron mass ratio. And you see, if alpha is changing, our clock states are changing. So if we compare two different clocks with respect to each other, we would be sensitive to such an alpha change. And typically, we give this a sensitivity coefficient that depends on the type of clock and transition I'm using. If you're very sensitive to alpha change, if you're sensitive to the mu change, these are more the microwave clocks or the molecular clocks. With a pure optical clock, you typically measure alpha. But you have to compare at least two clocks with different sensitivities. And a very nice clock that has two clock actually an atom that has two clock transition with very different sensitivity happens to be the ytterbium ion that you have in Pune. We have it at PTB. And the nice thing is we have many clock transitions. We have this electric quadrupole transition, and we have electric octupole transition, E2 and E3. And they're very different because the quadrupole transition is just an excitation of an S shell electron to a D shell, while the octupole transition is an excitation of an F electron very close to the nucleus, actually hidden inside the last valence shell. And it's opening up to a whole state and filling up the S shell. So first you have one electron in the S, now you close it with two electrons, but you leave it with a whole state in a F shell. So these are very different. And for this reason, you have very different sensitivities, not only to external effects, but also to this alpha. So the alpha sensitivity coefficient for the quadrupole transition is 1, while for the octupole transition, it's almost -6. And this is actually one of the highest sensitivities you can get nowadays. Of course, we can dream of highly charged ion clocks, thorium nuclear clocks, but they don't tick yet. Yeah? At the moment, what you have ticking on the planet is the ytterbium clock here. So people are using this, and what can you do? I mean, I don't have to plan for a very expensive space mission. I can actually use the Earth as my space shuttle. So this is the sun, this is the Earth, and within a tropical year, I'm orbiting around the sun in a rather eccentric elliptical orbit. And thanks to that, you can see that the gravitational field that we sense on Earth during 1 year is varying by 10⁻⁻10, just by this elliptical eccentric orbit. So you can search for an effect, gravitational change of 10⁻⁻10, and see how your clock is responding to this. And this is what people have been doing for many, many years. So you see the noise, you're drowning in noise, but you're trying to fit some signal. But at the moment, the measurements are always consistent with 0. But the error bars are getting tighter and tighter. And actually, the best measurements are now in the 10⁻⁹ region, just by comparing different optical clocks. In particular, for instance, the world record is kept now with the ytterbium ion, octopole versus quadrupole. And you can also do another analysis of the same type of measurement when you compare again ytterbium octopole and quadrupole, or ytterbium against the strontium lattice clock. It's again just a clock comparison, but now you evaluate it in terms of high order frequency components, the noise that you measure at different frequencies. And you see already clocks are very slow. Yeah, so these are very slow frequencies. But what it would mean, there are certain types of models suggesting that there would be a variation of the fundamental constants with the Compton frequency of this dark matter, which is coupling. So this is the density of the dark matter coupling to my system. And then I would see the Compton frequency of the new scalar field. And that's why we can push the bounds of these models further and further with our clock measurements. And you see the dysprosium measurements that have been carried out by Dima Budka and many other more measurements. There was a beautiful measurement by the NIST in Boulder, the Bacon measurement, where Giller and NIST on the other side of the road compared their clocks over a small fiber network. That was the world record in 2021. And very recently in 2023, it was overtaken by the PTB measurement of the ytterbium octopole to quadrupole measurement. You see, you make up again more than 1 order of magnitude, and you're eating out. The exclusion plot is getting better and better. So far, nobody discovered dark matter. And on the long term, this is of course the vision. When you're building now your fiber networks, you could dream of having what I showed you before: PTB, CERT, NPL, Italy, all Europe. I mean, you could dream of realizing a super detector by putting more and more clocks together. Also inside the UK, they have the QSNet consortium connecting all clocks in the UK. And this is like now an endeavor, but it needs, of course, a lot of funding to operate these fiber links. But that would be a vision to really connect all optical clocks worldwide to search for possible deviations, because honestly, not all clocks are ticking at the same time. You always measure for a very finite time. To really have something that you can call a detector, the uptime has to be close to 100% and on different regions. Okay, now I have 30 minutes left, including questions. So now I want to switch over to not long haul clock comparisons or clock to clock. I want to elaborate a little bit on fundamental tests with precision spectroscopy in a single ion. So what everyone can do if you have a tabletop experiment with a single ytterbium ion. And the first example I want to show you is the test of local Lorentz invariance, which is really remarkable. And at the moment, we're holding the world record at the 10⁻21 level. This is close to Planck's scale. And that's really remarkable because it's such an old experiment. It started in 1881 in Potsdam. The first time Michelson was doing this interferometric measurement was here in this tower in Potsdam, close to Berlin. You can still see the mock-up of his old experiment, where he tried to search for the aether as the preferred direction in the universe. And LLI means basically, or let's say if LLI is violated, then it basically means that the electron dispersion relation is modified. So that means the energies of the bound electronic states vary with velocity and orientation in the gravitational potential of the rest. So what does it mean? So if you have an electron shell and you have some certain preferred direction, so let's say it's not a spherical electron shell, but a p state, a d state, so you have a certain expectation value in one direction, like a quadrupole tensorial momentum, then this energy of this bound state should vary with the orientation in space, in a solar celestial space. If Einstein is right, it doesn't, then it's really isotropic. So this is actually what Kosteletsky put in his standard model extension. He's like the godfather of tests for a standard model. He's trying to make it more standardized and systematic. And this is what we're heading out. So this is, as a reminder, the old-fashioned, good old optical Mach-Sender, too much atom interferometry, the good old Michelson-Morley interferometer with light. And now people have started doing it with electron waves. Yeah, not light waves anymore, but electron waves. But it's the same type of experiment. So you have to search for an electron orbit and give it two different preferred directions, either by choosing the quantization axis or by rotating your experiment. Of course, it's not easy to rotate your experiment, but again, our space shuttle is doing it for us. The Earth is rotating. Once in a sidereal day, and that's 23 hours and 56 minutes, the Earth is rotating around itself. So we only have to be patient and wait. So what we do, we prepare actually the electronic state into this on an octopole transition onto the F state, which has a lifetime of 1.6 years. So it will not decay. And then we pump, we create a superposition of two different states, a m-1/2 and a m-7/2 state. You see that has very different preferred directions in the universe. And if something is wrong with general relativity, that would mean that the energy difference between these two types of M states would vary over the course of a day while the Earth is rotating around itself. So you have to measure the energy difference. Not so easy. So let's put this in the framework. Don't worry, I will not dive into the theory. I just want to show you that this is actually sorry, I have to drink something. I want to show you that this is actually a tensorial shift. So the way Kosteletsky implements it in the standard model extension. So this is by introducing this C matrix into the Hamiltonian. So this Hamiltonian violates LLI. It breaks the symmetry because you have a tensorial operator here, and this is the expectation, this is the momentum, the electronic momentum distribution, the quadrupole moment of it. And you see quadrupole moments break the symmetry. And basically, we have to measure this, but we can't really discriminate whether something would be wrong in the electron or something would be wrong in the photon sector, because the Coulomb interaction between the electrons, so the energy levels of the electronic state, is of course mediated by photons. So you can't differentiate that. That's why you put everything into one tensor component. But it would be already great to see anything. So that's why we don't matter. This tensor that we have to measure, that gives us the energy shift, has been calculated by Chuba, Flambaum et al. And here you see that ytterbium is by far the most sensitive atom that you can get. Calcium, barium are orders of magnitude smaller, and the F state in ytterbium has to date the highest sensitivity. So it's really good to measure. And again, don't worry about the equation, Wigner-Eckert. But what I want to point out, since it's a tensorial, a quadrupole moment, you have to deal with the M state, and they scale with M squared. So this is the signal will go with M state to the power of 2. Now this is unfortunate because it means we have to deal with M states, and M states are first order Zeeman sensitive. It's not so nice for an experimentalist because it makes us very sensitive to all kind of noise in the laboratory. And that makes it a really, really challenging experiment to suppress the first order Zeeman shift noise. Well, smart people have thought about ways to suppress it, and they have used means of quantum metrology to prepare the atomic system in a decoherence-free subspace, like Hartmut Heffner in Berkeley has used correlated and entangled calcium ions, 2 of them, and he prepared them in this entangled state so that the effective M is 0, then you don't have any noise problems. However, calcium is not very sensitive, while ytterbium is much more difficult to entangle on this crazy octopole transition. And if you scale up the number of calcium ions that are entangled, then they decay so quickly that you don't win anymore, because you're limited by the finite lifetime of calcium, which is 1 second, and the entanglement decays with n times the number of atoms you have. So This is really the big killer. I mean, Hartmut tried it, but even 4 ions were worse than the gain in 2 ions. Then Eckhard Pike and Niels Huntemann tried it by comparing really operating independent clocks, but that's of course very heroic because you need 2 big clocks at the level of 10 to minus 18 in your big lab. So not everybody can afford that. And they measured for half a year and had different quantization axes. While we wanted to do it in a simple way, now in a single ion, and break the record, but just not operating a clock, not a clock at 10 to minus 18, just a single ion. And the way we did it was we prepared the electron here in the manifold of the F state, and then we do RF Ramsey spectroscopy. We stretch out the global spin and turn it around this M manifold. We bring it to the stretch states and turn it back, and we try to measure the linearity of this energy spacing. And we want to see if something changes in this energy spacing ladder scheme over the course of a day. And that's very scalable and very simple because you don't even need a clock. You just need a single experimental ion system. So how we did it, we first had to excite the octopole transition. That was our first PRL in 2020 because nobody had seen coherent qubit manipulation on the octopole transition, which has really a deadly forbidden matrix element. So a pi pulse takes on the order of 50 milliseconds, which is like 100 times longer than in any other qubit system. So you really fight the decoherence. But now what we do, since we can excite the atom, we prepared, the electron is shelved to one of these metastable states. Then we make a pi/2 pulse. We distribute it in a Ramsey sequence, which is the dark time here. And then we close the Ramsey sequence with another pi/2 pulse and bring back the electron to the ground state. And then we fluoresce and detect electron shelving. But in between, something funny happens. And this is what we call a RF composite pulse sequence. And this is just to keep the system in a dynamically decoupled state and prevent it from dephasing and prevent it from decoherence because of magnetic field noise, because we want to have a very long coherence time. So even worse, I mean, since this is not a 2-level system, this is really an 8-level system. You see when you do Ramsey spectroscopy, the peaks are very sharp. It's like an echelon, a Fabry-Perot echelon. It gets sharper and sharper and sharper. So that makes it very sensitive to our spectroscopy. And just a glimpse what we're doing. So what we call this composite pulse sequence is actually this sequence on a Bloch sphere. Maybe this is easier to understand. That's a generalized spin echo sequence. Maybe, I hope you're familiar with the spin echo. You bring your Bloch vector onto the equator, a Ramsey scheme. Then you wait for a long dark time, and then you bring it back or up. But usually during the waiting time, you have all the noise problems. And then the Bloch vector is not one vector anymore, but it's opening up and you have many, many possibilities. It's completely dephasing. So what the spin echo does, it just rotates the Bloch vector manifold by 180 degrees by a pi pulse. So when it was dephasing like this, you rotate it and then it's rephasing again. Yeah? This is why it's called a spin echo. But that was not good enough. We tried it in the beginning and it didn't work. Our noise is so bad and we wanted to go to super long coherence times. That's why we needed 10 pulses and we do boing, 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 really a ping pong game on the Bloch sphere to cancel any possible intensity noise, frequency noise, magnetic field noise. And by doing this, here you see the stability plot of a simple spin echo sequence. And this is the UR10 sequence that we're using. These are pulse time errors, detuning errors, and this is much, much better. And I should tell you also, the number of pulses that we're using are 10,000. Yeah. And that's why any fidelity that is not 99.99% kills you. So every pulse has to be perfect. So I was saying optical clocks don't care about fidelity. Here we do. This is all about fidelity. Yeah, if you need thousands of pulses. And yeah, this is how we did our measurement. That's actually the signal expected according to the quadrupole shift, which is also a tensorial quadrupole moment, of course. So we put ourselves here, where the slope is maximum, and this is then the signal we are looking for during the rotation of the Earth. And I should say, thanks to this crazy UR10 sequence, we were able, you see here the scale of seconds, Ramsey dark time. In total, we achieved a coherence time of 2.5 seconds. And that's actually a factor 10,000 larger than without the pulses. So if you don't do anything on the Bloch sphere, if you don't do any dynamic decoupling, your coherence time will be a factor 10,000 smaller than what we have seen by doing this dynamic decoupling engineering. This is really the big gain of this Ramsey spin echo sequence. So that's really world record. And with this new dark time record, we then in 2022 started out doing a 5-week measurement. Very heroic PhD students and postdocs in my lab ran the experiment with a very high uptime. And you see, then you do a Fourier decomposition, a Fourier analysis. This would be the sidereal day and 2 times the sidereal day, because half a rotation of the Earth is also, of course, counting. And you measure down to the millirad regime. But the signal is still way below significance. So all the matrix elements that we could measure now are in a 10 to minus 21 level, and all agree with 0. So within the sigma that you get. I mean, this is world record now. And we have also improved the old world record by a factor of 9 times more sensitivity. And it's also a true scalable system. We're close to Planck scale now. So in the future, of course, we want to improve that. But yeah, I mean, as I said, it's absolutely remarkable. Why is Einstein always right? We don't know, yeah? You can do what you want, bring it to the Planck scale, and the sky is right. But I showed you because it's a nice experiment also that shows you how quantum engineering, especially with the Bloch sphere, can really give you this high sensitivity, and you can push the bounds beyond classical measurements. So now the remaining few minutes, and then up to discussions. I want to also show you another measurement that we did. Because we just had it, you know, we had a terbium system, we had a terbium-172, which is the even isotope. An even isotope means you don't have any nuclear spin. So it's a very perfect system. And as it happens, a terbium has 5 stable isotopes. So nature gives us 5 stable even isotopes. And we're doing precision spectroscopy anyway, so we thought, okay, let's look for dark matter as everybody does. And one thing you can do it, you can search for new bosons via isotope shift measurements. So how does it work? Scary transparency, but it's basically about king plot measurements. Maybe you have heard this in nuclear physics. So here in this picture, an isotope has a neutron extra. Yeah? So 1 neutron, 2 neutrons, more and more neutrons coming up. And many theorists, especially the ones that are predicting this new scalar fields coupling to standard matter, that should also then give some different energy shifts the more neutrons I have. So if I go from one isotope to the other, I should see different eigenstates, different energies in my atom. But of course, the ab initio calculations would never be precise enough to allow us to compare. Yeah? So we need to prepare differential measurements. We have to differentially measure one isotope with respect to the other and then go to more and more neutrons and see what happens. And this is all about the king plots that nuclear physicists invented. Actually, it is used to deduce the radius of the nuclear size, r squared. But this equation tells you that if you plot now, this is the difference between different isotopes, then you have something like the field shift and the mass shift, yeah, because it's a many body system, a 2-body system. So if the mass is changing of the nucleus, then also the energy is changing of the electron. Then the field shift is basically how much your electronic wave function tunnels into the nucleus and feels the field gradients there. So a lot of atomic physics, but you never can calculate it to a high accuracy, so you want to recheck it. And these things are actually all about doing, putting up linear equations with unknowns. And the more unknowns I have, the more equations I need. Yeah? And then I have a linear system and I can get rid of the unknowns. And hopefully what remains would be the dark matter. So if we look what are the unknowns, so if I make such a king plot measurement, so the differential measurement between the isotopes, I have here, that's the field shift contribution, mu is the effective mass. So this is immediately rejected by just comparing two different transitions in an atom. I can get this, but now I have higher order effects. Maybe my nucleus has a R⁴ moment, that's called the Seltzer moment. Maybe it has a quadratic field shift, not only a linear, but also quadratic higher order field shift moment. So you can think of higher and higher order moments. Of course, at a certain point, they will be ridiculously low, but we think the quadratic field shift is still significant, and also something like the nuclear shape, the Seltzer moment, but nobody knows it. So you see, we have already 4 unknowns, and then the big unknown, that can be this possible coupling to the dark matter. And this is what we want to see. So yeah, we have this equation of linear equations, but many unknowns. So we have to measure many isotopes and we have to measure many transitions to reject all the unknowns. And that's what people do. So Trillium Berengut has this very nice publication where he compared now the different measurements done and what he proposes to do. So calcium has been measured at that time with 100 kilohertz accuracy, and this is the exclusion plot they could do. So that's the coupling of the electron to the neutron. And this is the mediator mass of the unknown dark matter field. So in electron volts by many orders of magnitudes. This is a log-log scale. But basically in calcium, they could exclude this upper part. Meanwhile, Michael Drewsen in Aarhus has pushed it further. So calcium is getting better and better. But we already see it has a fundamental limit because it's not so sensitive like a terbium. If you resolve the king plots or the frequencies in calcium with 1 Hertz, you're still an order of magnitude worse than in terbium if you have 1 Hertz. Again, a terbium being so heavy and so many neutrons and so relativistic is one of the best sensors for dark matter. And these are some exclusions from astrophysics, from cosmological models. So what people have been doing, Vladan Vuletic at MIT in Boston, he started doing king plot measurements with the terbium ions and the even isotopes. He used the 435 quadrupole transition, the 411 quadrupole, but they are very similar. So you don't learn so much because they're very similar to transitions. But very cool is when you compare it to the octopole because it's a completely different quality, this transition. And in this recent 2 papers in 2022, Vladan achieved an accuracy of 300 Hertz here and 500 Hertz on the octopole. So 300 was the quadrupole and 500 was the octopole. And that is up to date, published, the world record. And he, for the first time, had an indication that the king plot, which should be linear, and it always has been linear in the past 30 years. But now, for the very first time in a terbium ion, Vladan saw some deviation. You see the residuals here. Within the error bars, they don't agree anymore with the linear fit. So he observed for the very first time a non-linearity in the king plot. And that means when you reject the mass shift and the field shift, there must be higher order contributions. We don't know yet what, but for the first time, people have been able to do such an accurate measurement that they see a deviation from the linearity of the king plot. So that's very exciting, yeah, because that means our tabletop experiments get now this resolution, this accuracy, that we really can do this physics. Since we had the same experiment at the same time, we also did spectroscopy on octopole and quadrupole. We do it anyway. So we're operating 411 and a 467 nanometer transition in our laboratory. And in 2022, we did measurements, but at the Hertz level accuracy. So 3 Hertz for the quadrupole and 16 Hertz for the octopole. So this is what we measured. And when we compare our measurements with Vladan's measurements, we see a bit of deviations. This is probably because of laser drift that he had. In principle, our measurements agree with Ladan in terms of the shape of the nonlinearities of this funny effects that he saw, but we measure an absolute different value here. So at PTB in our group, we compared it to the reference of Eckhard Pike and Nils Huntemann to the clock, to the terbium clock. So we didn't have drifts. It was for us better. And then we improved the accuracy by a factor 100, and we see small discrepancies, but the overall shape agrees. And in Kyoto, the group of Takahashi is doing neutral terbium. So wonderful, because now we even get more transitions. Yeah? We can kick out even more unknowns. So in the end, what you do, Julian Behrengut calls it a generalized king plot. So you reference your transition relative with another transition. And actually, the very good transition is the neutral transition at 578 nanometer in neutral terbium. So this is used nowadays as the reference. So everybody who measures now terbium divides it by the Takahashi value. And then you make this generalized king plot, this lambda plus, lambda minus, or these deviations. This is basically what I showed here. Is it like such a C deviation or such a zigzag deviation? So that was a proposal by Julian Behrengut, and this guy is really brilliant. You know, he collaborated also with Ladan in a data analysis. He's a theorist. And this is how can you get the best out of your data? You have now many measurements, many isotopes, many transitions, but how do you evaluate it? How do you reject the unknowns? And that's why Julian came up with this generalized king plot. And you see what you plot here relative to Takahashi's value. These are now the PTB measurements, red and blue, and the MIT measurements in grayish and yeah, yellow and green. And in this generalized king plot, we can reject quadrupole shift, mass shift. And if there was only one unknown, all the data points must lie on this yellow line. If there was only a quadratic field shift, which we don't know, then you would have expected that our measurements would lie on this line, but they don't. You see the residuals again? It's even not agreeing with one contribution. So there must be a second contribution on top of the quadratic field shift. And actually, since our PhD students and postdocs improved it now by a factor 100, the measurement, we have now a 87.6 sigma confidence that there is a second nonlinearity source, something we don't know yet, but on top of the quadratic field shift, there's a second nonlinearity source. This is, we can tell for sure. We don't know yet what it is, but it is there with a very high significance. And at the moment, we're collaborating with the nuclear physicists, in particular the Max Planck Institute in Heidelberg, the group with Klaus Blaum, and then Achim Schwenk, who is a brilliant theorist at GSI in Darmstadt. Achim is doing nuclear structure calculations. And Klaus Blaum, that fits very well to Martina's talk. Martina introduced this penning trap experiments where you measure very precise masses. Actually, Klaus broke another world record, and we're just about to publish this with him together now. The manuscript is in preparation. So he pushed the mass uncertainties of the terbium isotopes to 10 to minus 12 now. It's really spectacular. Yeah, so because we were limited, in fact, by the unknown mass. When you do this isotope shift measurements, at a certain point, the unknown mass changing from isotope to isotope was the problem. But thanks to the penning traps and the Max Planck Institute of Nuclear Physics, we have now new data, and our new improvement by a factor 100 in the lines in the frequency spectroscopy will be published now this year. And then it will be exciting because we have to continue working with the theorists, and probably I will learn a lot about nuclear physics, about the shapes of the nucleus. But it's really the first time that doing high precision spectroscopy is sensitive to the shape of the nucleus. And I'm really excited what we will learn. And with this, I'm at the end of my talk. Time for questions left. I thank all the people contributing, and if you have questions, visit us at our webpage, talk to me, or visit us in Braunschweig. And yeah, thank you for your attention.
Questions?
Yeah, so I did not understand the conclusion of the last part of the talk. So if from the isotope shift, do you find, so So there are ion measurement, atom. I think Budkar also has done some measurements, right? So is the conclusion that the king plot is not linear and there is something which we don't understand, or?
Yeah, and I mean, you see here the data, it is clearly not linear, yeah? This would be a linear line, but of course the deviation is tiny. But now if you zoom in, this is 10 to the minus 5. These are the deviations. Everything should line up at 0, but you do get big deviations. And actually the error bars are so tiny that they're smaller than the points here. So it's highly significant that this isotope king plot of the 411 and also of the 467 is highly nonlinear. And this is what people have never seen before, to really have this deviation. And that means when you look at these equations, just give me a second. So the king plot would only be linear if you have only the field shift and the mass shift. Any higher order contribution, like a Seltzer moment or like a quadratic field shift or dark matter, would give you rise to a nonlinearity. And this is what we try to bail out now by doing generalized king plots. We're working there with the theorists and high energy particle physicists, also doing a lot of hypothesis statistics and so. How to treat this data now? I mean, if you have 5 isotopes, you need to measure minimum 4 transitions, and then you can reject 3 of these contributions. So this is our state of the art. 1, 2, 3 we can reject, but 4 and 5 for unknown. I would love to go to IISER and CERN and actually use the even radioactive isotope. There's one, a terbium isotope, which has a lifetime of 60 minutes. So it's not long enough that I can bring it to Braunschweig. But if I bring the experiment to CERN, IISER, I could actually eliminate another one. That would be wonderful. But this is the stage where we're struggling right now. We have eliminated 3 contributions and 2 are open.
Hello. Yeah, ma'am, you have talked about different clocks at different gravitational potential has error of the order of 10 to the power minus 18 per second. So what about the different clocks that are rotating in an orbit around the sun at different distances? So they also have some error of?
Yeah, you mean our satellite system, for instance.
Satellite system.
That's a huge shift, yeah. This is why we have many brilliant relativistic theorists who are calculating our navigation. Yeah, if you're doing GPS, you must know relativity by heart, because you do have all funny shifts, not only the gravitational time dilation, but also the motional time dilation, lens tearing effects, and all crazy effects you have never seen in general relativity. This is very important for navigation. Otherwise, yeah, what I get in my mobile phone, my position would be completely off. And actually, this gravitational time shift is known for a long time. I mean, there were always funny experiments, like Braunschweig is close to the sea level. We're at 70 meters above the sea level. And then when we compare even our cesium fountain to the United States, yeah, the Boulder Nest is in the Rocky Mountains, 1,600 meters. Denver is the Mile High City, so 1,600 meters high, and we're with 70 meters. So we have a height difference between Boulder and Braunschweig of 1.6 kilometers. And this is 10 to the 13. We see that immediately. Only by comparing our cesium fountains, we always had to encounter for that. Otherwise, we could not even provide you time. Yeah.
So do we get any benefit due to the rotation of the clocks? Because
benefit in what sense?
So by rotation, the satellites don't see any gravity due to Earth. So
no, but the gravitational potential is always there.
Yeah, gravitational potentials are there.
I mean, and then the time dilation shift due to motion just adds up on it, and also all the other higher order effects that you have, like lens tearing and all that.
Yes, thank you.
By then, I may quickly ask again back to what Shura was asking. So this 87 sigma, isn't it a discovery, or is it does it put bound on the other 2 points?
I would say we can now not speak of an exclusion plot anymore. We have an inclusion plot. So what we will publish in our paper will be actually an inclusion with a bound here. And then you can see, okay, maybe some parts have been excluded by other measurements. So what is left? So we do see a signal, that's for sure. But again, we have to be careful because probably my feeling is the quadratic field shift is what we eliminate, but the Seltzer moment, you know. The problem is when you have very heavy atoms like a terbium, you're far away from the stability diagrams in the nuclear chart. So this magic nuclear numbers. And that can happen then that when you go from isotope to isotope, just adding one nucleus, that you slightly deform your shape. And that means that the R4 would really change. So that can happen. And that's why we collaborate now with the nuclear physicists.
Yeah, so besides the absolute number, it seems like there's an agreement in the shape of the deviation between yours and Vladhan's, right? So does this correlations tell you what you expect in the shape?
I think he simply had a, Vladhan, I think, simply had a problem with the clock laser. We discussed with him a lot. In the beginning, they thought, no, not possible. But that just happens because, you know, when he's doing isotope shift measurements, he has to switch the frequency. So he has to unlock the boundary-Hall lock, go to another frequency and lock again to the same cavity. And of course, he did a very thorough and very good job in predicting the drift of the cavity, which is also highly nonlinear. But then you can have rest amplitude modulation and funny effects when you lock with a boundary-Hall lock on a cavity that can shift your frequency. And that can happen then when you go from resonance to resonance. While we at PTB had the advantage that our reference was the atomic clock in another building, so there was no drift. So when we were going from isotope to isotope, we always had a very stable reference. And I think that was our big strong point.
So the shape is not real. Yes.
The shape is real. The shape, so the conceptual shape that this is like a C shape and this is like a zigzag, like this. This shape is real. It's just this deviation here was probably a measurement error. But I would really trust our points. Yeah, I mean, in the beginning I didn't trust them, but we verified them now over 2 years and repeated and repeated and repeated. So it's really there.
Yeah.
To check the clock performance, so we are like tally or comparing our clock with the different species. And when we are comparing it with a different species, then the main transition frequency is changed. So is there maybe that some error will be introduced by doing this one? And
so you're speaking of your experience, your measurement?
No, ma'am. From the data you showed that you were telling that strontium ion clock to the ytterbium ion clock. So, but they are two different species, and the main transition frequency is different.
This plot that I showed when there was the funny jump, you mean that one? Wait a moment, I will go back to see if it's on the same page. Is that what you mean? The ytterbium strontium measurement, how it changed? And that there's like a blob, and actually they've seen it again. I mean, this only goes up to 2021 or 20, but now in 2022, when we repeated the measurement with the triangle, then strontium and ytterbium have seen the jump again. It happened again. I mean, you can tell it's dark matter flying through, we don't know. But it's also likely that something goes wrong, maybe with the beat signal. It can be anything, you know, a clock, you have the estimated error budget on paper, but if a tracker is wrong, if something on the frequency comb in the arm path length goes wrong. I mean, of course, but they have really tested everything. It's really a bit of a bizarre thing. I mean, they are very good experts and they've really searched for every possibility. So I'm really curious what it will turn out to be. At the moment, no, I'm not saying anything more.
Okay, I think let's continue the discussion and let's thank Tanja one more time for doing the talk.